In this section of Chapter 8, I would like to go over types of bonds and lattice energy. Chemical bond is nothing but force of attraction that holds atoms together. Now the three basic types: ionic, covalent, metallic. Within covalent, one would be, I would discuss what is called polar covalent. So let me write down this right beside covalent. We're going to discuss that at a later time toward the end of this lecture. And ionic bond is due to electrostatic attraction between different ions. Covalent bond is due to sharing of electrons, and polar covalent is due to unequal sharing of electrons. So we'll talk about that. Metallic bond mostly you'd find in metals, and in this case electrons are loosely bonded, and that's why we have characteristic properties of metal. We'll begin with metallic bond. Now we know what metals are. In periodic table you have mostly metals. On the left hand side of metalloids or borderline elements. Now electrons in the metals move freely, but they're not very strongly bonded, and because of this loose bonding, those electrons can be readily promoted from lower level to higher level, and when they come back it gives off light, and that's why metals look so shiny. For these loose electrons, metals are also good conductors of electricity and also heat. In heat case, of course, it transfers heat quite quickly. That's true for almost all metals because they vibrate and then they transfer heat energy from one end to the other end. Metals are malleable. It is not going to crack. So basically when you try to bend it, those loose electrons readjust, and that's why there'll be no crack in the metal. Now I already defined different types of bonds. Now let me show you the formation of different types of bonds. Like in case of sodium chloride, we have sodium plus and Cl minus, and that's ionic bond. Covalent bond is due to sharing of electrons, like two hydrogens with one electron each can come close together and make a bond like this, and that's covalent bond. Similarly, 2Cl can make covalent bond. 2 bromine can make a covalent bond by sharing of electrons. Energetics of ionic bonding. Now let's consider formation of sodium chloride from sodium and chlorine. From sodium you get sodium plus. In order to remove that electron, 496 kilojoule of energy is needed per mole. On the other hand, when Cl gets the electron and forms Cl minus, 349 kilojoule of energy can be obtained because that's an exothermic process. But if you add these two quantities, it's going to be endothermic process. However, we know formation of sodium chloride from sodium and Cl is a highly exothermic reaction. So we are missing something in here. Now what are we missing in here? What is known as lattice energy. So first you make sodium plus from sodium and Cl minus. Then many of these ions, sodium plus and Cl minus, in crystal lattice structure, they attract each other, and altogether that attraction becomes predominant, and overall the energy releases is much greater than need of energy for the formation of sodium ion. So here we now define lattice energy. It's the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. So in case of sodium chloride, you separate sodium chloride into sodium plus ion and Cl minus ion in the form of gas. An amount of energy or change involved would be called lattice energy. Now, what kind of interaction energy we're talking about here in case of lattice energy? So if you have charges of ions Q1, the other charge is Q2. So Q1, Q2 divided by D is the distance between them. And that basically gives you the energy associated with electrostatic attraction between ions. And K is a constant. This is well-known Coulomb's law. Now here you're looking at a lattice structure of sodium chloride. You can see that sodium plus is surrounded by Cl minus and Cl minus is surrounded by sodium plus. And all these interactions added together makes this reaction highly exothermic, because only one first step needs energy, where you're making sodium plus from sodium, and then electron affinity of Cl makes it exothermic, and lattice energy is also exothermic. Here you're looking at lattice energies of some of the ionic compounds. Let's first try to understand the variation in lattice energy values. If you look at lithium fluoride and lithium chloride, now in this case lithium is lithium plus, let me show you, lithium plus, and in case of fluoride it'd be fluorine minus. So this lattice energy 1030. On the other hand, if I have, say, let's pick lithium iodide, lithium plus and I minus, it's much smaller. Now why is that? Always first you need to think about the charge. If charges are the same, say this is my positive charge, which is 1, negative charge 1. In all these cases on the left hand side, you have plus 1 charge and minus 1 charge interacting each other in the lattice. Now why is the variation? If you look at periodic table, between lithium and chloride, fluoride and chloride, you'd find that it's the fluoride which is much smaller than chloride, and chloride is much smaller than iodide. So basically you're looking at, in one case, plus 1 and minus 1. So in case of lithium fluoride, let's draw those. So lithium would be like this. So this is lithium, that's plus 1. Fluoride is pretty small, like this, that's minus 1. In case of the lithium chloride, lithium size would be the same, but chloride is bigger than fluoride. In case of lithium iodide, lithium would be the same, it's the same lithium plus. So let's draw it about the same, plus 1. Now iodide is a lot bigger. But what we see, lattice energy is much smaller. That means interaction energy is much smaller. Why is that? Here there is no charge difference. Charge-wise, interaction is between plus 1 and minus 1. However, the distances are not the same. When you have a bigger ion, the distance is greater. So remember we talked about that energy calculation, Q1, Q2 by R or D. So you have Q1 times Q2 divided by D. D is the distance. If I have a larger distance, interaction energy, which is lattice energy, is going to be smaller. And that's why this lattice energy value goes down when size of an ion increases, because that would automatically increase the distance between the interacting ions. Now then, what is going on the right hand side? In right hand side you have plus 2. Magnesium, strontium, they're all plus 2. So magnesium plus 2, this is plus 2, reacting with Cl minus 1, and there are 2 such Cl. So Cl minus 1. Now always plus 1 minus 1 interaction would be less than plus 2 minus 1 interaction. So always plus 2, no matter how big is the size, because usually the charges dominate over the size. But within the same charges, then you look for sizes. So now in this case, magnesium chloride, when I'm comparing with lithium fluoride, you can see that lattice energy for magnesium chloride is significantly larger, or magnesium chloride in comparison with lithium chloride. Why? Because positive charges would show greater attraction for negative one than positive one interacting with negative one. So lattice energy increases with the charge on the ions and also decreasing size of ions both. But dominant would be the charge carried by the ions. For the same charges, then you look for the sizes. Let me now go over problem number 26. So that's 8.26. The question is asking for an explanation of trends in lattice energy. A, lattice energy, so let's write down lattice energy of sodium chloride greater than rubidium bromide. That lattice energy is greater than cesium bromide. Before you answer these questions, look at periodic table and get an idea about the size. Among the metals, sodium, rubidium, and cesium, they belong to group 1A. Sodium is on the top, and then after potassium, then you have rubidium, which is bigger. Then cesium is bigger than rubidium. So we are talking about, even though these in each case is a +1 and -1 interaction, so the difference is not in the charges, it has to be in the sizes. Because we mentioned about two factors in determining lattice energy. One is the charge. Charge effect is usually more dominant effect. If same charges, then look for sizes. So sodium and Cl, if I write down sodium chloride, if this is sodium ion and say this is chloride ion, rubidium would be bigger than sodium, so let's call it sodium. This is rubidium +1, and bromide is bigger than chloride, so this is bromide, this is rubidium. Similarly, we can say cesium is even bigger than rubidium, so that's cesium, and it's bromide. Okay, this is Br minus. This is cesium, and this is Br. Let's forget this. This is +1, this is -1. Let's write down in a different color to be more visible. This is rubidium, and this is bromide. Okay, so now +1, -1. Now what we see here, the sizes of ions are getting bigger. As size is getting bigger, the distance between the interacting ions is also getting bigger. You can see here. Of course, these are not drawn to scale. So distance between sodium and chloride is the shortest one, and cesium and bromide is the largest one. As distance is increased, interaction energy is decreased, because remember we mentioned about this interaction energy as Q1 times Q2 over D. D is the distance. When distance is increased, energy is decreased for the same Q1 and Q2 values. So this is Q1 and Q2 values. So that's how we can explain. Because of the size, sodium and Cl are much closer, so they're interacting much harder, and cesium and bromide are much bigger and farther apart from each other, and that's why the interaction energy is smaller. and that's why lattice energy is largest for sodium chloride, and then rubidium bromide, and then cesium bromide. For part B, let's now try part B. Now they have given you barium oxide lattice energy greater than potassium fluoride. Again, barium is from group 2A, so it would have +2. So this is +2. Oxygen is from group 6A, is 2- or -2. Potassium is from group 1A, is +1. Fluorine is from group 7, is -1. So in first case, interaction is between +2 and -2. And that's much stronger than +1 and -1. So here side effect would be less important than the charge effect. And that's why just solely on the basis of charges, we can say that barium oxide would have a larger lattice energy than potassium fluoride. In part C, they have given you a lattice energy of strontium oxide, SRO, greater than strontium chloride, SrCl2. Again, here we see that in strontium oxide, you have a strontium ion of +2 interacting -2 on oxygen. In case of strontium chloride, strontium is +2 interacting -1 on each chlorine. So obviously interaction energy is larger for strontium oxide because +2 -2 interaction energy much larger than +2 -1. And so lattice energy is larger for strontium oxide than strontium chloride. Again, we see that charge effect usually is greater than size effect. So you look at size effect only when charges are the same on ions. Here we're going to define electronegativity. Electronegativity tells us about the ability of atoms in a molecule to attract electrons to themselves. Now, if you're looking at periodic table, electronegativity increases as you go from left-hand side of periodic table to the right-hand side. So that's the regular trend. Normal trend is this way, electronegativity increases. As you can see all these numbers underneath the element, like lithium is 1.0, beryllium is 1.5. So this is how it goes. And also electronegativity is increased as you go from bottom to the top of a periodic table. So most electronegative elements are the rightmost ones. Obviously, noble gases don't show any electronegativity. So you can see here fluorine get the largest number, which is 4.0, and accordingly others are numbered based on how strong that element is compared to fluorine. So when you have phosphorus or arsenic, electronegativity value of 2, that means it's about half as strong as fluorine in attracting electrons. Now let's assume that sodium contributes one of its electrons for bonding, and Cl does the same thing, one of its electrons for bonding. Now let's examine which one is more electronegative. From electronegativity table, I can get these values for you. Sodium is 0.9 and chlorine is 3.0. So there is a big difference in electronegativity. So Cl is more than 3 times stronger than sodium in pulling electrons. What that means is this electron pair would be going solely onto Cl. And Cl becomes Cl minus, and sodium would lose its originally contributed electron and become sodium plus, and that would give formation of ionic bond. Here we are showing you the same in terms of number. If you get the electronegativity values of sodium and Cl, and the difference is 1.9, such a big difference forms ionic bond, because first they're going to get separated into positive and negative ion. And so whenever there's an electronegativity difference of more than 1.9, the bond formation is considered to be ionic bond. On the other hand, if there is no electronegativity difference, like between two hydrogen, when the difference is zero, the type of bond would be called covalent bond. In between these two extremes would be called polar covalent bond. Now this is the polar covalent bond, where you have a positive end and a negative end, and the distance, and the dipole moment is defined by the charge on each end times the distance between them. In this slide, you're looking at compounds like HF, HCl, HBr, HI, and their electronegativity difference. In case of HF, the difference is the largest, 1.9, followed by 0.9 for HCl, 0.7 for HBr, and 0.4 for HI. So obviously, as you can see, that H remains the same, but side of the anion gets bigger and bigger, and which is the biggest factor in this case is electronegativity. Electronegativity difference, when it's the largest, dipole moment is the largest, you can see. And when it's the smallest, dipole moment is also the smallest. So polar covalent bond and its polarity is primarily determined by electronegativity difference.